So we'll proceed to that theorem. We know real analysis, but we'll see, in real, when you learned about real analysis, real functions, we know that if a function is analytic, you have a Taylor series, right? But such things are valid even for complex functions. All these things we have to go through. We have lots of theorems that we have to go through before we get to this central theorem, which is called Cauchy-Riemann theorem. So what is complex function? How do you represent a complex function, right, first? Z itself is a complex variable. So a complex variable, you know how to represent, or complex numbers, you know how to represent, right? We can simply write it as x plus iy, which is the real part of z, and y is nothing but the imaginary part of z. Okay? And this is normally represented in the Argand diagram, right? Theta is this. Let's call this the real part of z, imaginary part. So this is some thing. And if r is the distance here, we can also represent this complex variable as r exponential of I theta, where r is nothing but square root of x squared plus y squared. Both are, this is perhaps you're normally used to, but most of the time in complex variable we'll be using this representation. Okay. Theta, of course, is nothing but, tan theta is nothing but imaginary part of z over real part of z. So theta is nothing but tan inverse of, we would call y over x, or basically it is really y over x, which is same as imaginary part of z. Over real part of z. Right. This is something. This complex function, so basically in any domain, we have to ask many things, okay? If it exists, if f of z exists, and its derivatives exist, in a domain R, which represents the complex plane, then f of z is called as an analytic function. Some books will call it regular function, and I think the other word which is used also is homomorphic. Okay, so you'll find all these mean the same thing, a regular. I think this is less and less used, okay, nowadays, but homomorphic, all these things mean, all it means is the function exists in a domain and its derivatives exist, then the function f of z is analytic. Okay. So that is, one of the things, what is this function? So also this function f of z in a domain could be single valued, that is, it has unique value at a point at z, or it could be multi-valued. This is another quirkiness of a complex variable. Okay. So you'll always see these words. If f of z is single valued and analytic, certain theorems are coming through. Okay, so so f of z could be single valued based on function of, I'll explain this to you in a minute. Multi-valued. It could be analytic, or there may be certain regions where the function blows up, okay, there are finite number of singularities in the domain where the f of z blows up in the domain. That could also happen. So then those points are called singularities, right? So f of z is analytic. Except for some singularities. Within the domain. So these are the words you'll come across, and we will explain on some of the, some of the Cauchy-Richter theorem. There's something where we do it when it has got singularities. Okay, so all these things are important. If it doesn't have singularities, you can have a Taylor series. But if it has something like singularities, the function f of z can be expanded in terms of a series called Lorentz series. So we'll talk about Lorentz series. So all these things will become, these terminologies, jargons will become important. Right? Okay, let us look at this function f of z, square root of z, okay, where z is a complex variable now. Z is a complex variable. I can write f of z then as, in this notation, if I use that, r a by theta square root of that, which is r. Okay? And that's what it means, right? Now what happens to this function f of, supposing it's too much sometimes. Okay. Make it worse, or no, that's the other one. Yes. So supposing this function is defined in this domain, okay, whatever the domain is I'm just taking like this. What happens for this function is that if I go around z equal to 0 once, okay, at r, for instance, at theta equal to 0, already it has a value r to the power of half. When you go around this once, right, the theta is 2 pi, and that is pi, so e exponential I pi is cosine plus cosine pi plus I sine pi. So what you get is the value of the function z is r half, or when you come and hit from here, it is developing a different value, which is negative r to the power of half. Okay. So it's a for the same point in z, it's not single valued. For the same point in z, in this point, it is developing two values, or any other point, in any general point. Of course, it is r, after one circle, one times it will be what, ri theta plus 2 pi, r half exponential I theta plus 2 pi of half, right? So you will have that exponential of I pi. So the value will be something like this, right? Any other location also, it will be this, and then this enable sign coming from there. Okay, so after one iteration or one time you go around, the value at this point will be negative r half exponential I theta, depending on where you are. But when you go around that 2 times, okay, the theta has become 4 pi, it will recover its original value. Okay. So that's why it's called double valued function. How many times multi-valuedness of a function depends on how many times you have to go around z equal to 0 to recover its original value at the same point in z. Okay, so this function has z equal to 0 is called branch point of the function. And you have to go for such a complex function, square root of z, or all any if it's not integer power, all of them function like this. Okay. 0 alpha, where alpha is less than 0, all of them will be multi-valued functions. Okay. I mean, but the degree of multi-valuedness may be different for each one of them, depending on how many times you have to go around that. So any function f of z, where alpha is less than 0, okay, is not an integer, where alpha is not an integer, okay, then it will have multi-valued, but it will exhibit multi-valued, it will be a multi-valued function, complex function. Okay. So similarly, a function like f of z, natural log of z. Okay. So if I put z equal to r I theta, because this is a complex variable, this is nothing but natural log of r plus I theta, right? What happens when you go around once or twice, thrice? I can never recover this value, because when you go around the second time, it will be I theta plus 2 pi, and keeps on it because we have it here. So natural log of c is infinitely multi-valued function. You cannot remove the multi-valuedness at all in this function. Okay, so that's an extreme case, because after one time it will be that, then it will be I theta. This will increase the phase factor. This will increase by 1. Natural log of r plus I theta. If you want to put it I theta plus 2 pi. It keeps on increasing. I can never get the original value. Okay.
So what's the difference between infinitely multi-valued and single valued?
Single valued is at every point it has got only one value, unique value. Okay. In this case, let's say let's call this equal to along the real axis this point, right? For supposing I had like just some function z which is complex variables, it will have one value only, unique value at every point. Whereas doubly, complex, what is it called? Complex function with two values at each point is, it's got double, what is it? Multi-values is 2 in that case, okay? I mean, in the other case, it will be, it depends on what the function is. Z to the power 1 over 3 perhaps has got 3. And how many times you also have to go around z equal to 0 to get the value, right? It'll exhibit 3 different values for something at a given point. Then that defines the degree of multi-valuedness of that complex function. Okay, so you also have to worry about degree of multi-valuedness. So one of the tricks used for something which is doubly valued or something like that, it is a problem only if I come back to that, return to the same point, right? So what they do is introduce what's called as a branch cut. This is just a trick basically. Alright, so the function has unique value along this branch cut on the path of your curve, wherever you're doing. It all along this, it has same value on this path, and it has one value on that path. So here it has the value r for half exponential I theta over 2, whereas on this branch it has a value negative square root of r exponential of I theta 2. Okay. So these are called as z equal to 0. Here is called as branch point. And these are called as branch cuts. They're like almost like barriers, so that you don't, cross the real axis in this case. That's what it is. Okay, so you'll see this concept again and again coming. But for now, you have to realize f of z could be single valued or multi-valued at a given point in z. Okay. This is done only to exploit, the theorem. Some of the theorems that we'll be doing applies for single valued function. So it allows me to apply the single valued, those kind of theorems by putting those branch cuts and stuff like that. Okay, you are forcing, at least along the path of your trajectory, the function has unique value. It doesn't have two different values on that path. Okay. Okay, so that's only a trick. Okay, I mean that is sort of called Riemann surfaces in complex. If you dig deeper into complex analysis, those are called as Riemann surfaces. All right, so this is just to give you some general idea of what we are trying to. What I want to talk about is actually Cauchy-Riemann condition for analyticity of a function. So if f of z is single valued and is analytic, then its derivative, then it's if it's analytic, we know derivatives exist. Okay. All right. So f of z is my complex function. So I write it in this fashion. It has got a real part, just as a complex variable has got real part and imaginary part. This is complex variable. And this is my real part of the function. This is imaginary part of the complex function. analytic, what it means is f prime of z exists. Okay, it doesn't blow up. The first derivative of the function exists. Okay, that's what it means. We know the definition of f prime z from real variables. We don't know that. Let's start applying it in the same way. So, and see what happens and what is the difference here. I can write it like this, as we normally would do. Limit delta z tending to 0. Right? That's the definition of derivative. I'm going, although z is a complex variable, I'm just doing that way. Now, what's the difference here? Delta z, what is delta z? It's complex, right? So delta z is what? Delta x plus I delta 1. I can write it like that, right? And delta z tending to 0, I can do it in two different ways, right? I can make it what? Delta x tending to 0, because we got two parts here, and I can put delta y identically equal to 0. I can have limit, I can take the limit that way, or I can say delta x is identically equal to 0 and delta y tends to 0. Okay, so let's see if the derivative exists and it's unique, the limit, whether you take, how you take the limit should not matter. It should be the identically the same. So that will give us some condition on analyticity of a complex function. Okay, so what happens when you do the first limit? What is that? Case 1. Let's call it case 1. Let's call the limit as L1 equal to limit delta x tending to 0, delta y identically equal to 0. F is a complex function, all right, so I can write it as u of x plus delta x, comma, y plus delta y, right, that is my f of this thing, plus I v x plus delta x, y plus delta y, that is your f of z plus delta y, minus u of xy minus I v xy, right, divided by delta x plus I delta y. I'm going to put delta x because I have put delta y equal to 0, okay, because I'm trying to do the first case. Okay, let me write down maybe, and then we can remove that. So delta y equal to 0, if I put that, I can get rid of that, right? When I start putting, I can, delta y is 0, delta y is 0, and this is 0. So this limit is then what? If I combine this term with that term, what is that? What is this?
It's the partial u with respect to x.
Yeah, in the limit, I should put, now just limit delta x tending to 0, right? We still have that. So the first term is partial u with respect to x, and what's the second term?
I partial y, or v.
V with respect to x, okay? So, so I have that result that L1, the first limit is nothing but partial u with respect to x plus I partial v with respect to x. So this is what the first limit says. Now the same thing if I did for L2, the other one, with delta x identically equal to 0 and delta y tending to 0. Let me write down the full expression first and then we can do it. So now it's the other way around. So we have this is 0, this is 0, and sorry, here I have this, right? So when I put that, now this one goes away. Okay, so that is 0, right? So the other limit is then the following. Let me call that limit as L2. Limit, now delta y tending to 0, because other one we already put 0. I can replace this by delta I delta y in the denominator, u of x y plus delta y minus u xy, and this term will become what? I dx y plus delta y minus dxy, and have in the denominator I delta y. So this limit gives me what? This is what? With a negative sign, right? I. Let me put like that, minus I partially with respect to that. And here I and I will cancel, right? So what is that? Partial v with respect to 1, right? So this is when delta x tending to 0, delta y equal to 0, and the other one, L2, is minus I partial u with respect to y plus partial v with respect to y. So this is what we get when delta x is equal to 0, delta y tending to 0. So if the derivative is unique, then these two expressions have to be exactly equal. So we can compare the real part, imaginary part with the imaginary part. So that gives us a condition for analyticity of a complex function. So what the Cauchy-Riemann condition. So compare now the real parts of L1. So that gives me partial u with respect to x is equal to partial v with respect to y, and partial of what? Partial of u with respect to y is nothing but negative of partial v with respect to x. So this is what is called as Cauchy-Riemann condition. That is, if for f of z to be analytic, a single valued f of z to be analytic, okay, they must have all, all these derivatives must exist. Okay, u and v are real and imaginary parts of your complex functions. Okay, so all partial derivatives must exist. And both conditions have to be satisfied, not one of them, okay? And both conditions have to be satisfied. Just don't stop at one of them is fine to say that f is analytic. Thank you. Alright, so I'm just going to give you two examples and just tell me which is analytic and which is not analytic. So which function is analytic and which is not analytic, or both are analytic? What is u here? What is u of xy in the first case? That's a real part of the function, right? So that is x squared minus y squared. That's the first thing. v of xy is 2xy. That's the first thing that I identify. And here, real part is just 2y. The imaginary part of f of z is simply x. The rest should be easy. First, just identify what's the real part corresponding to that. So partial u with respect to x is 2x, right? Partial v with respect to y is 2x. Okay, the first condition is satisfied. And what about the second condition? Partial u with respect to y is negative 2y. And the next one is I have to do partial v with respect to x is 2x. And I have to satisfy this condition. Partial is negative of 2dx. So this is also satisfied. Both are satisfied. Okay, so this case f of z is analytic. And it is single valued because it doesn't have x to the half, square root of half or anything, right? It is x squared. Those are single valued functions. It has every, so f of z at every point has unique value. Okay, so it's already a single valued function. What about this? What's happening here? Partial u with respect to x is 0. Partial v with respect to y is 0. So this condition is satisfied. Okay. What about the next one? Partial u with respect to y is 2, and partial v with respect to x is 1. So this condition is not satisfied. Okay. So both have, you have to check both. Don't stop at just one. Both have to be satisfied. So this function is not this complex function, right? All right. Yeah.
I think I'm struggling to understand when it's single valued.
Hmm?
I think I'm struggling to understand when we have a single valued function.
So, yeah, single value function means at a given point in the Argand diagram, f of z has one value. That's one value only. At a given point. If you move to a different point in z, it'll have a different value. That's fine.
Okay.
It's not uniformly the same.
Yes.
Okay. So, like the way we went around, I mean, in that circle square root of z, you know, along the real axis at a given point, it had developed different values, right? R2 of half minus r. But if you go into a different location, it was R2 of half I theta over 2 or whatever it was, different, right? I mean, but what it means at a given point, you don't know, I mean, you know, like which value to take. It has got two values or more than one value. So it doesn't have a unique value at a given point in the complex plane for a complex function. Okay, so that's what we mean by single value or multiple values. Basically, at a given point, it's got multiple values, you know, which are, so it's not unique. That's all it means.
Oh, okay.
Okay.
One thing, to function to be analytic, we need to satisfy both the condition. In the first example, in the second condition, du over dy equal to minus 2y.
Maybe mistake, du over dy,
Divided 2x. du.
dv over dx is 2y. I made a mistake in terms of writing it. That's all. Yeah. I'm taking the derivative with the x, so it's 2y. Yeah. So that's condition 6. Alright, so we keep on building on whatever we learn. I mean, this is how it's going to be. You have to know the first theorem to build the next theorem, and so on and so forth. Okay, so all of them are important. So the next thing which we want to discuss is one of the Cauchy's theorems. Okay. One of the Cauchy's integral formula, and some of them will understand the differences between them. Okay. So what it tells you is the following. If f of z is analytic in a given domain and also on the contour C, contour integral of f of z dz is equal to 0. Okay, the contour integral closed curve, that's it. Okay, we know. So this thing says if f of z is analytic, that is it exists and its derivatives also exist. Okay, in the domain. Then the contour integral of f of z is 0. Alright, the only thing that you understand here is the word analytic. At this point, we know what it means. Okay, this is what we have done, and we know then the real and imagined part of f of z, should satisfy Cauchy-Riemann condition. That much you know, right? That's all we know. Okay, let's see. I mean, how I can prove this. Right. This is a complex function, so I can write this as it's got real part and an imaginary part of the function. And dz is a complex variable, so I can write it as dx plus I dy. Alright, this much I can do. Alright. So I can write integral of contour integral of f of z dz is, let me have all the real parts in one, uxy dx, okay, and minus vxy dy. Okay, plus I okay, and then plus I uxy dy. All I've done is separated the real and imaginary bodies onto integral. Okay, so that's all I've done at this point. Okay, just check it's okay. Ux dx minus vxy dy, okay, plus I pull the I out, right? Vxy dx and I uxy dy. Okay. Alright, so right now I can do nothing because my Cauchy-Riemann condition is on the partial derivatives. Do you know any theorem that converts from your vector calculus a line integral into surface integral? Do you remember?
Stokes.
Hmm?
Stokes.
Green's theorem, divergence. Is a divergence theorem in two dimensions is called Green's theorem. Okay? Stokes is from volume 2. This is a line, we are converting a line integral into a surface integral. Okay. So we have to apply, convert this line integral, this is from vector calculus, okay? What is called as Green's theorem, I'll write down that if you some people forgot what that is. So it converts, this is like a single one-dimensional integral, right? So you go from one-dimensional integral to two-dimensional integral, that's what we want to do. And I will write down that theorem so that so that's coming from vector calculus. It's an exact thing. The word I can, you don't have to worry about it. What it means is, if you have a region and you can, contract the circle into under one, without any obstacle, that's called simply connected region, okay? So that's what it means. But what you have to really know is P and Q and the derivatives exist in the domain, okay? If this is true, then contour integral of, or line integral of P dx plus Q dy is given as surface integral. Okay. So the domain is, C is just on that surface, on the contour. R includes the contour and the entire surface domain. Okay. There is nothing but partial Q with respect to x minus partial P with respect to y dx dy. Alright. So that is the theorem from vector calculus. Okay, I mean, so you just have, if you don't know it, just take it for granted. This is it. So, but all we are going to do is apply this to that, then I can get the, that. So what I have is uxy. So if I, for the first integral, my p is really nothing but, p corresponds to uxy, right, in the first one. And q corresponds to minus vxy. Okay. So I have to convert this into a double integral. Okay. Dx dy. Now what should I write here within the parentheses? Partial q with respect to x, right? Q is that minus partial v with respect to x minus partial u with respect to y dx dy, that's the first term, plus this term, right? I also have this, which is plus I double integral in the domain R of whatever I have to write down here, dx dy. Okay, so the second one here, p dx, right? So p is v, q is u. So that's fine. So that integral becomes what?
Partial u, partial x.
Partial u with respect to x. And the next one is partial v with
Partial v
respect
with
to?
respect to y.
Yeah. So that's what it becomes. Right. So this is what our f of z dz contour integral has become. Now from Cauchy's residue theorem, what do we know? I mean, Cauchy's the Cauchy-Riemann condition, we know that partial u with respect to this, these are equal if this term is 0. Okay. And we also know that partial, so this is, okay, yeah, that's the first one. And then we also know that partial u with respect to y, yeah, so when I take the other side, right, this is same as that. You can take that as minus, this is same as what? Partial u with respect to y plus partial v with respect to x equal to 0. This condition becomes that. So it's negative of partial u with respect to y plus partial v with respect to x is 0. Okay. So this term is also 0 from the Cauchy-Riemann condition. So we apply Cauchy-Riemann condition. So what it tells you is that if f of z is analytic, that is, it doesn't blow up anywhere, it's continuous everywhere. It has no singularities in that domain. Its first derivative exists. Then if you go along a closed path around that domain, it can be this, it can be smallest, it doesn't matter, okay? F of z, all it says is a closed path is equal to 0. So that is your Cauchy's theorem. Right? So this has got many implications. So I'm just going to call this corollaries of this Cauchy's theorem. As follows the on there. So I have f of z is analytic in this bubble region of whatever I drawn, and also analytic. Within the region. Okay. So I'm going like this. Doesn't have to be circle, right? This theorem says closed loop. Right. So basically I can say, you know, A to B, B to A, this, you know, this whole thing is zero. This my contour here includes C1, C2, both of them. So this is zero. So this C I have broken it down into two parts, right? I mean, I have a path A to B, f of z dz, right, plus B to A, f of z dz equal to 0. This is along C2, this is along C1, right? So according to that. Okay, fine. Then what does that in turn say? It says A to B, whether you evaluate this line integral, now it's not even contour integral, line integral, A to B fc dz is negative of B to A f of z dz. Okay. Or I can change the thing. So it's A to B along this on C2, this is along C1. So whether you traverse along C1 or C2, the value of the integral is the same. It depends only on the endpoints. Doesn't depend on the detailed trajectory, how you go from A to B. Okay, this is on C2, right? So we had a closed path, so it had. Now what it says is this theorem, the net result of that is the value of the integral A to B on C1 is same as value of the integral when they went along this path. It depends only on the endpoint. So it doesn't matter if you change to this. Okay, it doesn't depend on the detailed shape at all. As long as I had originally a closed path loop, the integral depends, value of the integral, this line integral now depends only on the endpoints of the function, as long as the function f of z is analytic. That's the key. Key here is this is only valid if f of z is analytic. The integral depends, the line integral in this case, depends only on the endpoints. Okay, let's further exploit this kind of argument. So supposing I have a function f of z is analytic on the big circle in this annular region and also on the smallest circle C2. Let me call it C1. Let me also traverse it anti-clockwise. In all these things, anti-clockwise direction is taken as positive direction in this kind of treatment. Okay, clockwise is negative normally. Okay. Let me call this as C2. And let me just even this way, and then AB, okay, and then C. Okay. So what we're told is f of z is analytic here, C1, C2, and I have a small slit here, okay. So how do I apply the Cauchy's theorem to this contour? Because Cauchy's theorem says that f of z requires only a closed contour. how do you interpret this? C here. We know f of z is analytic everywhere, here, there, you know, in this annular region on C2 and everything. How do I apply this theorem?
The integral of A to B, B to C, C to D, D to A, added together are the 0.
Yeah, but we also have to be careful about the signs and everything, okay. So yeah, the path is, the contour is everything, all the pieces, right? I mean, so we can say, contour integral on C1, right? I mean, it's, because assume this slit is very small, okay? F of z, dz, and we are traversing that in the counterclockwise direction, right? So I have that. Then I have C to D, that's a line integral, okay? F of z, dz. Then I have this is in the clockwise direction going, right? I mean, that's clockwise. Is it clockwise? No, that's not clockwise. This one's clockwise. That's the one, yeah. But here I have to draw it like that. F of z, dz, plus a to b, f of z, dz, equal to 0. So my C here has got several components on C1, A, B, C, D, and all these parts are there, okay, I mean C2, all of them. Now, if this slit is small, then these two, they are in the opposite direction, so they will cancel each other, okay, this and this integral will cancel. And what it says is, this integral says, theorem now says is, f of z dz on the bigger circle, okay, traverse along, now, let us say it was counterclockwise, right? I mean, counterclockwise direction. So I'm sure we like this. Counterclockwise direction is equal to negative of this in the clockwise direction, but I can absorb the negative sign and change it to plus. Right? Both of them traversing in the same direction on C2, f of z dz. Okay? So what this theorem says is f of z is analytic in the annular region. Whether you calculated the integral on the bigger circle or the smaller circle doesn't matter. They have the same, but you have to traverse in the same direction. You know, if you're traversing in the counterclockwise direction, the value of that integral, it should be that. Okay, same direction. Yeah.
Should one of those be C1?
What do you say?
You have them both written down as C2.
This one is negative, right?
Yes.
And I converted that, but that was in the wrong, that negative sign, I had changed it to the positive, you know, it was clockwise before, and I changed that to anti-clockwise here. That's the difference. This is, I'm rewriting that expression as that. So what I have is, f of, this theorem says, or corollary says, f of z dz, if you traverse, whatever that, you know, let's, if you traverse in the same direction, they all have to be traverse in the same direction. The value of those integrals are exactly the same. Okay, so how much time I have? Okay, I've got a little bit more time. Okay, so I want to talk to you about here. Right, because they all follow from the same thing, so let me do it today. this theorem says is the following. Let me just write down the theorem and then I'll prove this to you. Okay, what this theorem says is the following. If f of z is analytic, this is between R and C some curve, and the value of the function at any interior point, z naught here is an interior point in this domain. The value of the interior point in the domain is solely dictated by the contour integral along C on the on C of this function f of z over z minus z naught. Okay. So okay. So what is the difference here? Your integrand here is f of z is analytic. This is analytic. What about the integrand in this case? The integrand here is f of z over z minus z naught, right? That's not analytic at z equal to z naught because that is going to blow up, right? So what I'm going to do is all the theorems are what thus far we have developed is for analytic function, right? So what I'm going to do is I'm going to eliminate the point z naught with this, by drawing a circle around it, then cutting that slit, and I'm going to draw a circle like that, C1, C2, I'm going to draw it like that. Okay, that eliminates. Now, if you eliminate the point z naught, then f of z is analytic in the annular region. Okay, so eliminated so I can apply Cauchy's theorem, all that stuff, also to this function, the one which is the integrand is blowing up. Now, so based on that, we just proved that what? If I eliminate it, then and the function f of z over z minus z naught is also analytic in this annular region. And what did we prove? We just proved value of the function on C1 of an analytic function. In this case, it will be analytic in this regime, right? I mean, on C1 is same as the value of the function if you traverse in the same direction is same as the value of the function on the smaller circle. You can do exactly the same thing and make it 0, but we've just proved it, so I'm not redoing that. So this is what we did on C2, and you have to traverse the value, this is what the theorem or corollary said. Okay. Now, I need to evaluate this quantity. Now, this is z naught, and let me call this as z on the circle, the complex variable is z, and let me call this radius as rho. What can I write? How can I write z minus z naught in the r I theta notation? what is z minus z naught? It's a complex variable, right? If the radius is rho times a exponential I theta. Okay, r I theta is of that. R could be the bigger circle. The variable z on the bigger circle, z minus z naught on the bigger circle is r I theta. Okay, this is with respect to, previously it was origin was 0, but it is z naught. So z minus z naught on the bigger circle is r exponential I theta. On the smaller circle is rho I theta. Alright? Now, so what we will do is try to make rho tend to, I want to evaluate this integral. What I'll do is, I'll make rho tend to 0 and try to see what I can get. Okay, so we know these two have to be the same. And let me just also write. Right, let's say it's on this, so I can write it as 0 to 2 pi now. F of z naught plus rho exponential I theta, and this is nothing but rho exponential I theta. dz then is nothing but, rho is constant, so it's exponential I theta, I. So I can write for dz, rho exponential I theta, I d theta. Okay. On C2, okay? So dz was rho exponential I theta. Alright, so I can cancel this, alright? And we're going to calculate this in the limit rho tending to 0, that is we're shrinking that thing. And so what do I get? What is that integral? So what is the value of this integral now? Rho tending to 0, this is 0. So this is nothing but 0 to 2 pi of f of 0 times I d theta. It becomes a very simple integral, right? Which is nothing but 2 pi I times value of the function at z naught. So that is a Cauchy's integral formula of this, which is f of z, f value of function at z naught is nothing but 1 over 2 pi I of right. So this is called as Cauchy's integral formula. Do you have time or some really?
Yeah, we can finish.
Okay. Maybe, or I can also start from here next time, because what I want to know, tell you is next time, what is the first derivative of the function at such a thing, or nth derivative. Those are important for me to get back to Taylor's series and stuff like that. You understand? I'm just the function analytic. What do we do normally? We write it in terms of the function in real variables, in terms of a and z minus z naught. The coefficient depends on the derivatives, right? So I want to prove the Taylor's series from first principles from this, all these things for you. Okay, so maybe it's a good point to stop at because I want to do, I can start from here. And what is the first derivative of a complex function at an interior point, or nth derivative at interior point, and from there on I'll try to develop the Taylor's, what is the Taylor series for a complex function, and then Lorentz, if it is not analytic, Lorentz series expansion. So I can go on with that. Okay. So maybe it's a good point to stop. So because there's already a lot of theorems today, so you'll have So the main thing you have to understand is analytic contour integral of f of z dz is 0. But that's not going to be the case most of the time. You then apply tricks like that. Oh, here it is. I'm going to eliminate that point, and try to evaluate the value of the integral around the small circle, and try to get the integral. It's just breaking up a big contour into smaller contour, things. All these things, all these little pieces become important when we do the infinite integrals. But let me stop here and, so just be careful because all of them starts with the name Cauchy, and you have to understand which theorem we are talking about. Okay, Cauchy-Riemann, Cauchy, the analytic one is Cauchy's theorem, this is a Cauchy residue theorem, Cauchy's integral formula. The guy did everything. Riemann and Cauchy did everything in this field, it seems. So you have to understand, based on what the question is, you have to understand the context.